Hello and welcome to my presentation regarding the paper Anticipatory Vehicle Routing for Same-Day Pickup and Delivery using Historical Data Clustering. My name is Kronmueller. I'm a PhD student at TU Delft. The work I'm presenting to you today was carried out as cooperation between TU Delft, ORTEC, and AirLab Delft. Why we worked on this problem is because we saw a trend that controlling transportation systems effectively raised over time or within the last years, and especially for dynamic and stochastic problem. And then on the other side, we see that more and more data is gathered, which can be used. And we try to combine the two for solving a dynamic vehicle routing problem in an anticipatory fashion using this historical data. The specific problem we looked at was a dynamic multi-depot pickup and delivery problem with time windows. Dynamic in our case means some requests are known in advance and some are revealed during operation. So that means the problem is changing over time while it's carried out. We first of all modeled our problem as a static problem. And to do so, we used a free index flow formulation adapted from Cordeau and Laporte. And we formalized it as a minimization problem of total travel cost. On the right, you see that formula, and it's also subject to 16 constraints to ensure the problem constraints. We want to refer here to the paper. Using this static formulation, we then adapt it such that we can model our dynamic problem. And we do so by adding a release time to each request. So time it actually gets known. And therefore, the static problem changes over time. And there is a need to consecutively solve the updated static problems. The contribution we do with this paper is first, we introduce a novel anticipatory insertion method. The general concept of anticipatory insertion I will explain to you shortly. Then it's based on historical data. So we are not relying on any assumed arrival probabilities or distributions here. And we test the approach on large-scale simulations and show that the method can scale up. So let's start with the general concept of anticipatory insertion. What you see here, you first of all have a set of known requests. And to that one, you get a second set of predicted requests. Those two are merged prior to solving and then given to the solver. The solver computes a solution for the joint set, which is then carried out in operation. And now you have placeholders within your solution, and those placeholders are either replaced by an actual request that's getting to be placed, or it's removed from the solution, and that's happening over and over again while the operation is carried out. Okay, that's the general concept, which we then apply in the following approach, which I tried to illustrate to you here. What you see on the left side, we have a part that's happening once at the beginning, and there's a part that's happening online repetitively during operation. The whole approach is structured with three different components: the predictor, the processing, and a solver step, which are highlighted in different colors. Don't worry, I will explain to you each of those components within the following slides. Let's start with the predictor itself. So the predictor is the part that's taking in the historical data, which is then clustering it, looking how often those clusters appear, and then it's generating actual predictions. For generating the cluster types, we use a hierarchical agglomerative complete linkage clustering, short HACLC, which is working the following. We start at the bottom, and each request is its own cluster. The clusters closest to each other according to some similarity measure are then merged over and over again until the similarity hits a given threshold where we stop. And the clusters that are the result of that step are the final clusters in one dimension. We did so over and over again over multiple dimensions like time or distance of the requests, which then gave us some request types. We then looked in that second step, how often do those request types occur within the historical data, and we used the concept of relative frequency of occurrence here. For each type, to represent it as prediction, we then use the mean of all requests that belong to a given type. These predictions are then given to the processing step. And the processing first has a component that's happening offline, and that's the addition of those predicted requests given by the predictor to the set of known requests at the moment. And then there's a second part of the solution of the processing step that's happening while the operation is happening. And there's once a replacing of predicted requests. Imagine a new request is placed. What we then do is we look, is there a predicted request within our solution that's similar to the one that got placed? And if that's the case, we replace the two and we insert the new request by a cheapest insertion approach in our case. And then there's a second case. We remove predicted requests that did not have a counterpart. And we do so for two reasons. Number one, the time is exceeded where it should have got known the prediction. And when a vehicle would start driving towards the predicted request, then we also remove it from our solution. As I already have been talking about the solution. The way to come up with this solution, that's exactly the part of the third step, the solver itself. The solver we are using here consists of 3 steps, and they are depicted here in that scheme. So at the beginning, we have a construction phase, which comes up with an initial solution. And this is then improved using a local search. And afterwards, we start running a ruin and recreate process. The ruin and recreate process is happening in parallel, therefore represented by those stacked bars. What I want to mention here, or to your attention towards is that red bar, which means vehicles are available or the operation is happening. And what you see here, that part is happening in advance, coming up with a first solution. And this solution is then changed during the operation using the ruin and recreate. How the 3 parts precisely work, I'm going to refer to the paper, or the papers linked in the paper, as that's not the focus of the talk I'm giving here. The next step is, after having this approach, we wanted to know how does it actually perform. And therefore we run some experiments, and those experiments were set up the following way. So we looked at an urgent delivery case of flowers in the Netherlands and Belgium. In the bottom, you can see the pickup and drop-off locations. We solved it for 10 different days, and each of those days we solved 10 times to get solid averages. One of those days consisted out of up to 1,650 requests and 500 available vehicles. The degree of dynamism was between 0.7 and 0.9. And while simulating, we checked every 30 seconds if new requests got placed and if they got added to the problem. To range in the performance of our algorithm, we compared to 3 other approaches. So on the next slide, everything that's dark blue is the proposed method. If it's in bright blue, it will represent our greedy approach, which was a reactive approach paired with a cheapest insertion. In orange, you see a reactive approach that's using the exact solver I showed you, and that's a close competitor to the proposed method we have. And then fourth, we implemented a full information approach. So an oracle that exactly knows what's going to happen, and it has all the information at the beginning. For all those approaches, we use the same implementation of the solver to make the comparison fair and really that the results contribute due to the change of the approach itself and not to some implementation. Okay, let's look at one result. What you see here on the y-axis is the distance, or more precisely, the expected distance. And on the x-axis, you see time. And what you see here, those two approaches, the two reactive approaches, they need very little distance in the beginning, as they only solve for the set of tasks that get known. And when there are more tasks they have to do, the distance they require is increasing. Compared to that, you see the full information approach, which is constant over time as it knows everything right from the start. And then you see the anticipatory approach in between. What you see here on the right is the actual distance that was needed over the 10 times we solved each day. And what you see here in red is actually the full information approach performs best and the greedy approach performs worst. Really interesting is when we compare the anticipatory approach to its reactive counterpart. And what we see is that the anticipatory approach performs best. Not best, better. The interesting question is how much, and therefore we wanted to look on the full 10 days that we solved. And what you can see here on the left is the distance that was needed compared to the full information approach. So how much more distance was needed than when you would have known everything. And what you see is that the greedy approach needs around twice as much. The anticipatory approach needs around 10% more distance on average, and the reactive approach on average needs about 15% more. When you compare the anticipatory approach directly to its reactive counterpart, we save around 4.5% of distance plus minus 3.5%. Which was a nice side effect that we found out is also that the anticipatory approach will need less vehicles, and that's around 3.5% less vehicles are needed to serve the same set of requests. What you see here on the right is have our predictions that has been done, have they been happening or did they just get removed? And what you see here in dark blue is the predictions that actually happened, and in orange, the ones which didn't, and you see them plotted against the relative frequency of recurrence. And to sum it up, on average, about 60% of all predictions have been correct over the 10 days, and that led to the improvement. This brings me to my summary. So the anticipatory approach outperforms the reactive close competitor by 4.5% plus minus 3.4% on average. We obtain solution close to the full information approach. On average, about 10% difference was seen. And then we also see that historical data can be used to predict future demand, and therefore it can be used to improve on reactive approaches. At that point, I want to thank you for your attention. If you have any questions or comments regarding my presentation or the paper, please feel free to contact me. My contact information you can see here on the slide. And at that point, I want to thank you a lot and enjoy the day, enjoy the conference, and goodbye.